Today I'll be sharing the method to access the spatial wave sub-epidemic framework model on the GitHub repository, as well as the different functions that are required to run the model, how to run the model, what are the input parameters, what is the output that we get, so on and so forth. So for the first step, in order to run this model, you need the MATLAB software installed in your computer. Once you have your MATLAB software installed in your computer, you need to access the GitHub repository, which is on the following link. And once you open this GitHub repository, you can see a bunch of files open up. There's one folder, which is a Spatial Wave Sub-Epidemic Framework Model folder, which contains all of the functions that the MATLAB requires in order to run the model. It also contains an input folder, which contains multiple different data files that are the input data files. And as you can see all of the data files basically say cumulative daily coronavirus cases, and they are set by the date. And they're separated each week apart. And then we have an output folder, which for now has some of the pre-stored output files that we get once we run the model. So in order to download this folder, you would have to go to this green icon that says code, download the zip file. Once the zip file is downloaded, you can go into your download folder, unzip it. If you just double click it, it just unzips itself. And once it is unzipped and it's in a normal folder format, what you have to do is copy and paste it anywhere on your computer that you want this to be accessed from. For me, the easiest place where I save all my files is within the MATLAB software. And hence you can see that all my codes are saved within the MATLAB, the spatial wave sub-epidemic model. So once you're within the MATLAB, you can see that there is an input folder, output folder, similar to what we had in the GitHub repository, and all of the functions that are downloaded in your MATLAB. Some of the functions just on a bigger level, telling you what each of the function comprises of, and then we will go in detail to each of the functions. The options.m function basically specifies the parameters that are related to fitting with the model, any of the characteristics of the time series data, the sub-epidemic model, so specifying what kind of model we're using, the parameter estimation methods, the error structures that we're using, as well as if we will be using any of the smoothing factors to smooth out the data to avoid any noise in the data. Then we have a function which is called the options.forecast function, which is right here. And this function basically specifies the parameters that are related to the forecasting, which includes the forecasting time period, the type of the ensemble weights, which are required for the ensemble models, and if we want the forecasts to be evaluated or not. Then we have another function, which is the run SW sub-epidemic framework. This function basically derives the top ranking sub-epidemic wave models to the data with a quantified uncertainty. And I will go in detail as I go through the code. And then we have another function, which is the plot ranking sub-epidemic framework function. And this function basically plots the mean model fits of the best or the top ranking models, including their sub-epidemic profiles and associated quality of the fits, providing us with the values of the AICs and the relative likelihood and the evidence ratio as well. And then we have the plot fit sub-epidemic, SW sub-epidemic framework and other function. And this function basically displays the model fit, the 95% prediction intervals, as well as the distribution of the parameters. And then we have the plot forecast SW sub-epidemic framework function, which displays the model-based forecast and its associated performance metrics. And then we have other smaller functions such as get AIC, which basically computes the AICs associated with a model fit, so we can assess which of the models performs the best based off of the lowest AIC values. We have another function which is called the get and params function. This basically returns the number of the fitting parameters. We have a fitting modified logistic function patch ABC, which fits a model to the time series data that we feed into the model. Then we have a fitting modified logistic function patch multiple.m. This file basically generates the uncertainty associated with a given model fit. Then we have a plot modified logistic plot modified logistic growth patch methods 1, which basically is an objective function defining the fitting of the model to the data. We have a modified logistic growth patch, which basically defines the sub-epidemic models for the numeric solutions. We have an add error structure function, which basically introduces a Poisson or negative binomial error structure to the model. And then we have a compute WIS, which basically computes the weighted interval score for the calibration period as well as the forecasting period. And then we have a compute forecasting performance.m, which basically computes a forecasting performance metrics for the calibration period and the forecasting periods. Then we have another function, which is basically the get mean variance function, mean variance ratio function, which computes the average of the variance to the mean ratios from the time series data. We have a compute quantile function right here. This function basically computes the quantiles from the uncertainty of the models separately, separate for the forecasting period as well as the calibration period. Then we have the get ensemble sub-epidemics. This basically derives the ensemble forecast from a set of top-ranked sub-epidemic models, however many we define in the actual code when we go forward. Then we have a num2ordinal.m file, which returns the ordinal of a number provided as the input. We have a get data file, which function, which basically returns the data as needed to evaluate the forecast. And then we have an xtick label rotate, which basically rotates the labels on our x-axis so we can turn them into a 90-degree or a 45-degree or a 180-degree, depending on whatever we want in our final figures. So now looking into the input files for our code, if you see, we have multiple different input files. Each of the files starts with cumulative daily coronavirus cases, USA, and then we have a different date. And these are all saved as a TXT file, which is a text file, which the MATLAB can very easily read as we define in our code as we go forward. So if we open up the TXT file outside of our MATLAB, we can see it's a text delimited file, and each of the column and each of the rows basically each of the row is one observation, and each of the column, which in total we would have 52 columns because we're using all the data from all the states. So each of the columns will basically be the number of cumulative cases for each of the states. And if you go forward, checking all the files, you will be seeing that each of the files is set up in a very, very similar fashion. Okay, so this is how the dataset files are set up within our input folder. Next, we will start going over the options.m function file. This function file basically defines the parameter values for the spatial sub-epidemic framework. The first thing that we do is we declare the global variables and we will be defining the global variables as we go down in our code. We will define the method, which is the method that would be used for fitting of the model to the data. Then we have n patches fixed, which is another variable that will tell us the number of the sub-epidemics. The onset fixed basically tells us when the next sub-epidemic is supposed to take off. We have a distribution function, which tells us what kind of a distribution we're using in our model. We have a factor one, smooth one, and calibration period one variable as well, and I will explain them as we go down in our code. So this file basically contains the first variable, which is cumulative 1, and we set it as equals to 1, and it basically indicates if the data file contains a cumulative incidence, which is if it's equals to 1. And if our data file just contains the incident cases, then we set it as equals to 0. Then we have the outbreak X variable, which basically defines or is an identifier for the spatial area of interest. So since we have 52 areas of interest or 52 columns in the data, that's what we're putting in here as 52 for outbreak X. Then we have the variable CAD date 1, which is a string which indicates the date for the most recent observation in data file. And the format for that will be month, day, and then the year. Then we have the variable CAD region, which basically indicates the geographic region of the time series data, and it contained in the file. So it could be Georgia, USA, Asia, world. So however you name your file. So if we go back into the input folder, we can see that we are naming each of these files as US, like the CAD region for each of the files is USA. Therefore, we're putting USA over here. If it was Georgia or it was New York, then we would just put Georgia and New York over here. Then we have the CAD disease, which represents the kind of disease that we're referring to. And again, all of these strings connect together to create the input file name. And that's what we're trying to import by giving the different names, by defining the different strings for each of these variables. So coronavirus is the disease that we're using, and the data type is the cases, which indicates the kind of the data we're using. If you're using mortality data, it would be deaths. If we're using hospitalizations data, it's probably going to be cumulative daily coronavirus hospitalizations USA, and then you would just put hospitalizations instead of cases over here. Then we have dt equals 1, and this basically defines the temporal resolution of the data, which means it would be 1 if there's a daily data, and it would be a 7 if it's a weekly data. So if our data is going on a weekly basis, then we will simply use 7 for our dt. And then we have CAD temporal, which defines if it's a daily incidence data, cumulative incidence, or a weekly cumulative incidence data. Then we have the two other variables, which are the date WEC first one and date WEC end. And the date WEC first one is basically a 3-value vector that specifies the date that corresponds to the first data point in the time series. And again, the format for this would be year, month, and day. And then we have the date WEC N1, which is a 3-value vector that specifies the date of the most recent data file. And again, the format is going to be the year, month, and the day. Then we get into some of the adjustments of the data if we think that the data requires some adjusting. We have a variable that is called smooth factor 1, and this basically defines the span of a moving average smoothing used to smooth the case series of data. If the smooth factor 1 is equals to 1, it indicates that we're using no smoothing. And the reason that we want to utilize this variable and use 7 is because we're trying to reduce the noise in the original data, which can arise due to artificial reasons such as the weekend effect. And by using a moving average of the time series, we basically avoid that noise, and we avoid the artificial noise introduced into the original data, such as due to the weekend effects, and therefore we're using smooth factor 1 equals 7 for this particular data file. Then we have a calibration period, which basically defines the time period that we are using to calibrate the models. So it's basically the number of most recent data points that we will be using to calibrate the models. And this by no means should exceed the length of the time series that is contained in the data file. So for the purpose of this model, we are going to we're going to use the most recent 90 days as our calibration period. Then we move on towards the parameter estimation and the bootstrapping strategy. So for this purpose, we are going to use, for the purpose of this model, we are going to use a nonlinear least squares method to estimate the parameters. And there is other kind of estimation methods, such as the MLE method that you could use. And it all depends on the kind of estimation that you require. And within the parameter estimation, you would be using some kind of a error structure, which would basically be a Poisson or a negative binomial error structure, depending on the kind of the data. And that will be basically defined by dist1. And this dist1 equals 0 means that we're using a normal distribution to model the error structure. And if we're using dist1 equals 1, then we're basically using a Poisson error structure, and dist1 equals 2 means that we're using a negative binomial error structure. After that, we have the parameters, which are the num start points equal 10, which is basically the number of initial guesses that we're going to use to, for the optimization procedure using the multi-start process. And b equals 300 basically means the number of bootstrap realizations we are using to characterize the uncertainty within our parameter estimates. So 300 bootstrap realizations means that it is going to run 300 times. If it is a b equals 200, then that means that this simulation will be running for 200 times. Then we define the spatial wave sub-epidemic model, which is the model that we are going to use within this tutorial. So the first variable defined within the sub-epidemic wave model is n patches fixed, and we define it as 3. And this is basically the maximum number of the sub-epidemics that we will be using to basically to be considered in the sub-epidemic wave model. And then we have the variable called top models X. And this is basically the number of best fitting models that will be generated to derive the ensemble models. And if we define top models X equals 4, then that means that there's going to be 4 top fitting models that will be utilized to generate or to derive the ensemble model. And if it's 3, then 3 models will be used to derive the ensemble model. And these 4 or 3 best fitting models will be based on the values of the AICs. After that, we define a parameter which is called the flag 1. And this basically defines the kind of the growth model which is used to model a sub-epidemic. So the sub-epidemic wave model can basically be modeled using multiple different growth models, such as the generalized growth model, generalized logistic growth model, generalized Richards model, holistic model, and just simple Richards model. And whatever model we are using to model the sub-epidemic is what we will define within the flag 1. So here we're using a generalized logistic growth model to model a sub-epidemic. So we're using flag 1 equal 1. And then after that, we have a variable that says onset fixed equals 0. And this is basically indicating the onset timing of the sub-epidemic at time 0. Or if we are not setting the onset of the timing of each sub-epidemic at time 0. If we're not, then we are going to use onset fixed equals 1. And then the type 2 decline basically tells us, this variable basically defines the exponential sub-epidemic decline function. And if we're using a exponential function, then we will be using 1. And if we're using a power law, as defined here, power law decline in the sub-epidemic size, then we will use 2 in our type 2 decline variable. So once we are done with this, we are going to go ahead and look into the next file, which is the options_forecast file. And this file basically is a file that allows us to define the values for each of the variables which will be utilized in the forecasting of our model. So the get performance one is an indicator variable to indicate if we want to compute the forecasting performance metrics. So throughout the model, we compute calibration performance metrics as well as the forecasting performance metrics, such as the mean squared error, mean absolute error, WIS, MIS. And in order to indicate we want them or not, we utilize the get performance metrics equal 1 to tell the model that we need the forecasting performance metrics. Then we have the delete temp files equals 0, and this variable basically is an indicator to indicate whether or not we want to delete the forecast.mat files. If we want to save them, we are going to use 1, and if we don't want to save them, we are going to use a 0. And then we have a forecasting period equals 30 is going to be the horizon or the time period that we want to forecast our model. And for this particular tutorial, we are forecasting 30 days ahead in time, and we are using a 90-day calibration time period. So that is what is defined right here. And then we have a variable which is called the weight type 1. And this variable basically allows us to specify the types of ensemble weights. Using this parameter, we are going to define the types of ensemble weights. So if we are using unweighted, then our weight type 1 will be equals to 1. If we're using equally weighted ensemble from the top models, that will be -1. If we're using ensemble weighted based on relative likelihood, based on the AIC values, it is going to be 1, so on and so forth. And in general, when we are going to use this function, we are going to be using the inputs as get the performance, delete temp files, forecasting period, and the weight type 1. All of these inputs that we just defined as variables will go in the function line for this particular file. After this, we're going to go ahead and look into the file that will be basically running the model, or the file that we will use to run the model. So the run SW sub-epidemic framework basically is the file that we are going to use and to run the model. And this file is going to use all of the inputs that we will provide via the options.m file within our model files. So we will run this framework, and this takes a little bit longer to run. So I have already run this prior to the tutorial. But going over this file, again, we define the global variables, which is the onset fixed, which we defined in options M, the distribution, Poisson or negative binomial, the factor 1, the smooth factor, and we use 7 as our smooth factor because we wanted to avoid the beacon effect. And then we also give the variable calibration period within this file, which is 90 days, and we defined it in options. So this function basically uses the outbreak X pass and then cat date 1 pass as its inputs. So we declare the global variables, we load the parameter values, which are supplied by the user, and the parameter values are named as cumulative 1 INP, outbreak X INP, cat date 1 INP, cat region INP. We're basically just using all of the inputs that we already defined in our options.m file. And as you can see, we just call them equals options. Then we define some of the dataset properties. So we define the if-else statements, that if the outbreak X pass variable equals 1, then we define the outbreak X equals to outbreak X pass. Otherwise, we define the outbreak X equals to outbreak X pass INP. That is defined as a parameter value supplied by the user. And similarly, we say the same thing for cat date 1 underscore pass. The cat region basically is indicating the region of the time series as defined earlier. The cat disease is in string indicating what kind of disease we're talking about. The data type is indicating if the data is cases, deaths, hospitalizations, and the DT INP is basically defining the resolution, the temporal resolution of the data. Then we give the cumulative 1 variable the name cumulative 1 INP as we are defining within this run SW sub-epidemic file. We define the DT cumulative 1. We provide name of the file where we are providing a string structure cat function, which basically combines the cat temporal, cat, which is the time, the cat disease, the kind of the disease we're talking about, the data type, which is cases, cat region, which was the United States, and then the outbreak X, which was the kind of outbreak, and then cat date 1, which was the date that we specified. So this is basically the name of the specified adjusted data file per the region. Then we define the first, the date WEC first one basically corresponds or defines the date corresponding to the first data point in the time series, and the date WEC end is basically corresponding to the most recent data file in the format. And again, the format would be year, number, month. Then we define the adjustments to the data if we have to in this file. And like I said, we already have done this in the options.m, so we do not have to do it within this file. We then go into the mathematical model where we define n patches fixed equals 1 and our top models X equals 1. We load and proceed to the parameter estimation that we have already defined within our options.m file. We select the calibration period, which is going to be 90 days. And this basically simply just defines the same 90-day period in a format where if calibration period is less than the length of the data, then the data 1 is to n minus calibration period 1 equals should be 0. And this basically defines as 1 until the end by each increment of 1. We remove all the early zeros until a non-zero data point is found in the time series, because if the data, the code just finds, or the algorithm just finds zeros, it doesn't really run. So we have to remove all the zeros if there are any in the beginning of the data. And that's what this index 1, data 1 time lags piece of the code is doing. And if the time series is too short, then we're just defining that we should not proceed further and we should just stop and end the algorithm. And then we just save the data file for further analysis. So this is the adjusted incidence data file that we get. And then we derive the best fitting sub-epidemic models, where we're just basically providing the code to plot the best fitting top models in a subplot format to see how the models look like. We also derive the uncertainty of the top models to see how the models have performed and what are the parameter estimates around the models as well. So once we have run the sub-epidemic wave model, we get multiple different outputs. And if you see in this output folder, there's like a whole bunch of different output files. So for instance, this will originate or generate ABC original and patches for files. And these files basically contain the fits from the top ranking models. And the names of the files contain the values of the parameters for the reference. So the modified logistic patch These files basically contain the uncertainty characteristics associated with each of the top ranking models, the modified logistic patch files. And the output on all of these files that are generated when we run the run SW sub-epidemic framework are basically then used to plot the model fits, write the parameter estimates, to generate our short-term forecast, as well as quantify the calibration and the forecasting performance metrics as well. So once we run this SW, we get all of the outputs, which are then going to be used to see how the model performs. So now, if we go into the plot SW, so here's plot SW sub-epidemic framework, we will see what we get in terms of all the fits of the top ranking models, including their sub-epidemic profiles, as well as the parameter estimates, the residual plots. And this is all based off of the parameters that we have defined in the options.m file. We also get this empirical distributions of the parameters associated with each of the top ranking models and the calibration performance metrics. So if you observe here, we get the total epidemic wave size as well as the number of sub-epidemics. If we start looking at these files, okay, so if you observe these files, we're getting all of these parameter estimates. So we get all of these profiles, which are associated with the number of sub-epidemics, right? All of these different profiles have the parameter estimates. The histogram shows the distribution, empirical distribution of the parameter. The red line shows the mean, this graph with the cyan lines and the black circles shows the overall model fit and the uncertainty associated with it. This figure here with the red and blue curves basically shows us that what is a sub-epidemic wave profile, and then these are the residuals, and we get these figures for however many top models we generated. So once we look at these, we can go forward and look at the figures where we get the number of sub-epidemics as well as the total epidemic wave size. And as you can see, it says third ranked model, fourth ranked model, and for each of the models, we get the epidemic wave size as well. And that tells us how the epidemic size looks like for us. And then if we look here, we get the performance metrics, which is basically the mean absolute error, mean squared error, weighted interval score, and the 95% prediction interval coverage. And we get it for each of the top ranking sub-epidemic wave model fits. And then we can look at the distribution of each of the parameters as well. So this is the R parameter, the growth rate. This is the A parameter. This is the Q, which is the quenching parameter. P, which basically tells us about the polymer growth pattern, and K, which is a final epidemic size. So we see for each of the models, what is the estimates of each of these parameters. So the plots SW sub-epidemic framework provides us with these outputs. Similarly, if we look at the plot forecast sub-epidemic framework and we run this file, we get the results for the forecasting period. So this will take a minute to run. So this will basically plot the short-term forecast from the top ranking models as well as the ensemble models that are derived from the top-ranking sub-epidemic models based on the inputs indicated from the options.m as well as the options forecast.m files. And we can also end up saving all of this data, the forecasting data, as a txt or Excel file for future purposes if you want to look at it. And then again, this function will also plot the forecasting performance metrics, how we saw the calibration performance metrics. This will spit out some of the forecasting performance metrics to see how each of the models has done in the forecasting period. So it's still running. So I'm just going to wait a little bit until it's run completely. Okay. So the first figure that we observe is basically the performance metrics figure. So we get the forecasting performance metrics for each of the ensemble models. As you can see, again, this is the ensemble model forecasting performance metrics for each of the top ranked models. Then this figure basically shows us the ensemble 2, ensemble 3, ensemble 4, and these are the ensembles that we get out of the top ranked models. And the top ranked models are as follows: the first ranked, second ranked, third ranked, and fourth ranked. All the time period before this the vertical dashed line is the calibration period. After that, in the red circles, is basically the data, and all the graph in between the two black lines, all the gray, is basically the different bootstrapping bootstraps of the forecasting period. So this time period, or this graph that is after the vertical line, is all the forecasting period for us, which was 30 days. This figure shows the sub-epidemic wave profile for each of the 4 top-ranking models. The gray graph basically shows the overall epidemic profile, and then how it is divided into the different sub-epidemics is what is shown by the red, blue, and green curves. So once we have all of these, we can assess how the forecastings have done across different models, which model does the best, so on and so forth. And we can also compare the performance of the weighted ensemble models by setting the parameter estimates. Let's see, in the here, where the weight type equals -1, if we want to use the unweighted ensemble models, and if we want to change it, then we can just change the -1 into whatever we want to run to, and we can just generate the newer forecast after we change the weight type into 0, 1, 2, or 3 based off of whatever we're trying to use the weighting scheme for the ensemble model. So this is how the sub-epidemic, a spatial wave sub-epidemic model can be run.